On the morning of November 18, 2025, the Chinese National Space Administration released a batch of high-resolution images taken by its Chang'e Deep Space Tracking Array. These weren't ordinary flyby snapshots. They were full-frame, layered time-lapse composites taken over an extended period, tracking one specific object moving silently across space, 3I Atlas. What the frames revealed was not only movement, but rotation. Subtle, deliberate, and consistent. This changed the conversation. Because for months, astronomers argued about whether 3I Atlas was tumbling freely, stabilized by mass distribution, or doing something altogether stranger. The Chinese photos answered part of that question, but opened up several more. So in this episode, we'll walk through what spin really means in space. Not just in motion, but in intent. Because if 3I Atlas is rotating, we now have to ask, why? Stay with me. Before we begin, hit subscribe and tell me in the comments, where are you watching from and what time is it right now? Every time you engage with this channel, it helps us dig deeper. Long before most of the scientific world had even finished processing the previous night's data, a quiet update appeared on the public server of China's National Space Administration. It contained no dramatic headline, no announcement, no press conference. Just a small collection of 7 high-resolution images, each marked with identical coordinates and identical framing. At first glance, it looked like a routine calibration sequence, until researchers realized what they were looking at. These were images of 3I Atlas captured by China's Chang'e Deep Sky Tracking Array, and they were unlike anything released before. What set these images apart wasn't their clarity, although that alone was impressive. It was their structure. The frames were taken at precise 5-minute intervals, each one stabilized against the same background star field using a triple-axis correction algorithm. This technique allowed the foreground object, 3I Atlas, to be isolated more cleanly than in most ground-based captures. Nothing in the frame moved except the object itself, and that is where the anomaly began. When astronomers compared frames 1 through 7, they noticed that a brightness zone on the object's surface shifted position in a steady arc. The movement wasn't due to trajectory change, parallax, or atmospheric conditions. It was internal. Something on 3I Atlas was rotating. The Chang'e array is built for this kind of detection. Its imaging system relies on 3 simultaneous exposure channels: visible light, infrared, and narrowband ultraviolet. Each channel captures a slightly different expression of surface texture and energy output. When the exposures are layered and processed together, they form a composite capable of revealing motion too subtle for traditional telescopes. In these new images, the composite enhancement revealed a clear pattern. 3I Atlas was not static. It was not tumbling randomly the way most interstellar objects do. Instead, it showed a consistent spin. A single surface feature moved across the visible limb in a way that matched rotational motion rather than drift or shadow. When the data was plotted, the rotation curve pointed to a spin period of approximately 6 hours. What made this so striking was the stability of the movement. Natural objects, especially elongated, icy interstellar objects, rarely rotate this cleanly. They wobble, they precess. Their motion degrades over time as outgassing or impacts transfer momentum unpredictably. But 3I Atlas displayed none of that. The brightness zone moved in a predictable pattern, with no signs of axial instability. It was as if the object's rotation were being actively preserved, or at least damped against natural forces. Chinese analysts included a short note in their release. It read, in translation, "Observed object displays longitudinal modulation consistent with structured axial rotation. Axis stability exceeds expected parameters for cometary bodies of comparable size." That single sentence sent shockwaves through research channels, because axis stability is not a phrase casually used in astronomy. Maintaining a clean, consistent spin requires either a very symmetrical mass distribution or active stabilization, and neither of those traits are typical of natural interstellar debris. Within hours, observatories in Europe, South America, and South Africa began cross-checking the Chinese frames with their own archived brightness data. Several had recorded minor fluctuations over the past week, variations so small they were dismissed as noise. Now, when plotted against the rotational curve revealed by the Chinese array, the fluctuations aligned perfectly. independent teams quietly confirmed that China was right. 3i Atlas was spinning, but the implications run deeper than rotation. If the object is spinning with this level of coherence, then it either formed with extraordinary symmetry, unlike any cometary nucleus observed before, recently acquired rotation from a force we do not yet understand, or is maintaining its rotation through internal structure or mechanism. Each possibility raises a different kind of question, and each one moves 3i Atlas further away from the category of ordinary interstellar object. The Chang'e images were meant to be routine. Instead, they opened the first chapter of a new mystery. Why is 3i Atlas spinning so cleanly, and what does that rotation reveal about its true nature? When the Chinese imaging array revealed that 3i Atlas showed visible surface rotation, the global scientific community had one immediate question. Could this motion be confirmed independently? In astronomy, a single data set, regardless of how precise, must always be cross-checked against unrelated instrumentation. Fortunately, there already existed a silent archive of measurements taken across nearly a dozen observatories over the previous 10 days. These were not images but light curves, subtle brightness records captured every night as 3i Atlas crossed the sky. Light curves are one of astronomy's oldest tools. Before high-resolution imaging, before spectral mapping, scientists used nothing but brightness fluctuations to determine the spin, shape, and reflectivity of distant objects. A rotating body reflects sunlight unevenly as its surface turns. Peaks in brightness reveal reflective zones, while troughs expose darker or more irregular patches. When plotted over time, this creates a rhythmic signature, an oscillation that reveals far more than the eye can see. For 3i Atlas, these fluctuations were faint. So faint, in fact, that most observatories had dismissed them as residual noise from atmospheric haze, wind gusts, or instrumental drift. But on the morning of November 18th, after China released its time series images, researchers began pulling those archived curves back into analysis. What they found was unmistakable. Across datasets from Chile, Spain, South Africa, and India, the same recurring pattern appeared, small but consistent. Each brightness cycle rose and fell with a periodicity matching almost exactly 5.9 hours. The amplitude of these waves was modest, no more than 0.06 magnitudes, but the timing was too perfect to ignore. The intervals between brightness peaks lined up not just with themselves, but with the rotational arc seen in the Chinese frames. This was not coincidence. This was confirmation. A brightness modulation this precise meant that something on the surface of 3i Atlas was rotating into and out of view at predictable intervals. But the more interesting detail was the shape of the curve. Natural comets, especially those with irregular, jagged surfaces, tend to have messy light curves. Their brightness shifts are uneven, chaotic, full of small distortions caused by jets, tumbling, or fragmented surfaces. 3i Atlas, however, displayed a remarkably clean waveform. Each rise and fall mirrored the previous one almost perfectly. Such regularity tells a deeper story. The object is not tumbling, but rotating around a stable axis. This axis stability is extremely uncommon for small interstellar bodies. Without internal structure or controlled mass distribution, rotation tends to devolve into complex wobble. Yet 3i Atlas showed none of this. The brightness peaks remained phase-locked over multiple nights, implying that its rotation vector was fixed in space. As these findings spread through astronomy circles, teams began applying advanced analysis tools to the data. Fourier transforms were used to break down the curve into harmonic components. If there were chaotic elements hidden beneath the surface, these would appear as irregular spikes. But the transforms revealed something surprising: a dominant primary frequency, accompanied by a faint secondary harmonic that repeated at a stable ratio. The presence of harmonics suggested that the surface of 3i Atlas was not uniform. It possessed at least two regions with distinct reflective properties, possibly smooth zones, possibly metallic patches, or perhaps structured surfaces that behaved more like panels than like naturally eroded ice. Another key discovery came from the phase angle evolution. As Earth rotated around the Sun, the viewing angle of 3i Atlas shifted slightly. If the brightness variations were mere observational noise, the curve would distort as angles changed. Instead, the curve maintained coherence across all observation windows. This meant the source of the modulation was intrinsic, not observational. Astronomers at the European Southern Observatory published a preliminary memo summarizing the findings. Brightness periodicity matches rotational banding. Light curve stability implies symmetrical rotation and absence of free tumbling. This statement, subtle as it was, carried enormous implications. A stable spin suggests structural regularity. Structural regularity suggests internal cohesion. And internal cohesion at this level is rare in natural comet-like bodies, especially interstellar ones subjected to millions of years of gravitational stress and thermal cycling. At this stage, no conclusion could be drawn, not yet. But the alignment between the Chinese imaging data and light curve archives offered one undeniable truth. 3i Atlas is rotating, and the rotation is not random. It is consistent, controlled, and remarkably clean. And when an object spins this cleanly in the vacuum of space, the next question becomes unavoidable. What purpose does this rotation serve? Rotation in space is inevitable. It's a byproduct of motion, formation, and interaction. Most objects that drift through interstellar space, asteroids, comets, fragments, spin due to impacts, uneven heating, or gravitational tugs over long timeframes. But their rotation is rarely smooth. Instead, they tumble. Their axes wobble unpredictably. Their motion degrades, shifting from symmetry to chaos. This chaotic tumble, known in physics as non-principal axis rotation, is the rule, not the exception. It's what happens when there's no internal stabilization, no correction mechanism to keep the object aligned. And that is what makes 3i Atlas so strange. After its rotation was confirmed through both image data and global light curve analysis, researchers began investigating a deeper layer of behavior, axial coherence. Was 3i Atlas spinning around a stable, fixed axis, or was it precessing, slowly drifting from one rotational state to another like most unconstrained masses? The answer came from a close inspection of multi-night observations, especially those that tracked brightness vector migration. The apparent movement of reflective surface zones across multiple spin cycles. In a tumbling object, these reflective peaks shift unpredictably. They decay, jump, or reverse. But in 3i Atlas, they remained locked. Frame after frame, the bright zones followed the same circular path, with no deviation in trajectory, orientation, or angle. Over a full rotation cycle, the reflective peak returned to the same spatial coordinate relative to the star field, night after night, regardless of Earth's position. That kind of rotational consistency is rare, even in Earth-orbiting satellites. Astronomers at the National Radio Astronomy Observatory ran vector alignment simulations using this brightness data. Their models showed something remarkable. The angular momentum of 3i Atlas appeared to be conserved with engineering-level precision. There was no axial drift, no measurable nutation, no signs of damping. Even when solar pressure varied due to shifts in radiation intensity or minor solar wind disturbances, the rotation axis held. To put this in context, every known natural comet experiences torques, tiny forces from outgassing or thermal lag, that gradually nudge its spin. Over weeks or months, these torques accumulate, causing axis drift. But 3i Atlas showed none of these deviations. Its spin direction remained precise within fractions of a degree, even across hundreds of thousands of kilometers of solar system travel. Two explanations were proposed. The first was improbable. 3i Atlas might be an unusually symmetrical object, with an even mass distribution and no significant outgassing. If true, it would have to be smoother, denser, and more internally cohesive than any known comet or asteroid. It would need to resist torque naturally, through shape alone. But no examples of this exist in the known universe. The second explanation was far more unsettling. Internal stabilization. Not necessarily intelligent, not necessarily mechanical, but some system, either in its structure or material composition, that actively resists wobble. This could include layered mass dampening, magnetic field alignment, or a gyroscopic core, all of which imply something very different from a typical interstellar rock. One observational clue came from the absence of chaotic brightness variance. In tumbling bodies, light curves often display double peaks or irregular dips as multiple surfaces rotate into view. 3i Atlas displayed only a single dominant brightness pulse. clean, centered, and repeating. That pattern points to a body with a primary face, a surface that rotates in and out of solar alignment without flipping or wobbling. In spacecraft design, this is called attitude stability. No current model of comet evolution predicts this kind of behavior spontaneously. For 3I Atlas to maintain this kind of axial lock across such vast distances and variable forces, it would need either anomalous internal damping properties or an origin story that we do not yet understand. By November 18th, observatories tracking the object had converged on a shared conclusion, published quietly in several internal memos. 3I Atlas displays axis retention inconsistent with natural rotational degradation. That phrasing was careful, it avoided speculation, but it stated something clearly. This object was not behaving like a natural comet, and when an object maintains perfect balance across hundreds of thousands of kilometers, when it spins cleanly without drift, and when it resists the very forces that shape every known body in space, scientists are left with only one rational question. What kind of structure resists the universe so completely? As soon as the evidence of spin became public, researchers turned to one of the most sensitive instruments available, the James Webb Space Telescope. Unlike ground-based telescopes limited by Earth's atmosphere, Webb specializes in capturing infrared wavelengths, allowing it to measure thermal emissions from cold, distant or heavily shadowed bodies with extreme precision. And what it saw on 3I Atlas didn't just challenge assumptions, it contradicted them. Infrared observations are essential for understanding the thermal behavior of any celestial object. When sunlight strikes a comet or asteroid, part of that energy is reflected, part is absorbed, and part is re-emitted as heat. That heat appears in the infrared spectrum and reveals how efficiently the object handles energy. In natural bodies, there's a predictable correlation. The brightest sunlit areas are the warmest. Temperature gradients follow solar exposure. The physics is simple. Heat in, heat out. But 3I Atlas did something else entirely. During a 72-minute observation window on November 17th and 18th, Webb's near-infrared spectrometer, NUSSPEC, recorded a distinct rotational pattern just as expected. The object's thermal output oscillated in a repeating cycle, consistent with its spin period of approximately 6 hours. But there was one detail that didn't make sense. The hottest regions didn't align with the brightest ones. This is not just an anomaly. It's a violation of fundamental thermodynamics. In all known natural cases, regions receiving the most solar energy will emit the most infrared radiation, unless something is actively interfering with the heat flow. At first, the data was dismissed as calibration error. Researchers rechecked the orientation, reprocessed the gain, and corrected for potential phase lag in the detector. But the discrepancy remained. The rotational peak in brightness occurred roughly 22 minutes before the peak in infrared. That delay was consistent, repeating across each spin cycle. It became known internally as the thermal offset gap. To understand what this means, consider a simple analogy. Imagine holding a metal plate in sunlight. The side facing the sun warms first. That's expected. But now imagine the plate rotating, and instead of the front heating up, the opposite side begins radiating more heat a few seconds later, without direct exposure. That kind of behavior implies heat is being moved, intentionally or otherwise, across the structure. And that's what 3I Atlas appeared to be doing. Further analysis revealed that the object's infrared profile was not uniform. Instead, it contained narrow thermal bands, zones of slightly higher temperature moving across its surface like waves. These zones were not fixed to a location, but migrated in synchrony with the object's rotation, like internal heat was being redistributed from one section to another. This opened up an entirely new theory: thermal regulation. In spacecraft design, this isn't unusual. Satellites employ reflective panels, radiative fins, or conductive pathways to shift heat across their surfaces. But in natural cometary bodies, there is no known mechanism for internal heat flow, especially not with directional preference or timing precision. Scientists at ESA's Infrared Processing Center in Darmstadt noted an even stranger pattern. The coolest zones of 3I Atlas were the ones facing the sun during rotation. That's the exact inverse of what's expected. If this object is passive, then sunlight should drive local temperatures up. but if it's actively redirecting energy, those sunlit zones might be reflecting light without absorbing heat, similar to low emissivity materials used in engineered radiative shielding. This brought another material possibility to the surface: selective emissivity. Some synthetic compounds can be engineered to radiate heat in narrow wavelength bands while reflecting others. These materials don't occur naturally, especially not in free-floating interstellar debris. The thermal inconsistency was so profound that NASA and ESA analysts gave it a designation, TDE1, or Thermal Divergence Event 1. As of November 18th, no natural explanation has reconciled all variables. The brightness remains stable, the heat doesn't, and the spin-driven shift in thermal signature behaves less like rock or ice, and more like a system regulating its own temperature. If this regulation is natural, it represents a new class of interstellar thermal behavior. If not, it suggests design. When astronomers study distant objects, they don't just look at how bright they are. They look at how that brightness is broken apart. Light, when split through a spectrometer, reveals structure, fingerprints of the materials and energy sources that produce it. Peaks and valleys in the spectrum tell scientists what elements are present, what temperatures dominate, and how motion or geometry influences the way energy is released. For 3i Atlas, spectral analysis has become one of the most important diagnostic tools. And in the days following China's confirmation of its rotation, several observatories began reviewing not just the timing of its brightness, but the composition of the light it emitted across a full spin cycle. That's when something unexpected appeared. Teams from the European Southern Observatory and the Tsinghua Astrophysics Group independently detected a phenomenon now being referred to as spectral band compression. The term describes what happens when specific emission lines, particularly those in the ultraviolet and visible ranges, narrow and flatten during rotation, rather than maintaining their normal, slightly broadened shape. To understand why this matters, it's important to know how natural spectra behave. When sunlight reflects off a rocky or icy body, it passes through layers of dust, gas, or surface roughness. This scattering causes line broadening, tiny shifts and distortions in the wavelengths as photons bounce, absorb, or refract in microstructures. It's not chaotic, but it's noisy. That noise is expected. It's how nature behaves. But in 3i Atlas, something else is happening. As it rotates, certain narrow bands of its spectrum become even narrower, compressed into tight, noise-free signals with defined edges and minimal scattering. These bands appear only when one specific face of the object rotates into solar alignment and vanish once that face turns away. This isn't how comets behave. It's not even how polished asteroids behave. This is optical selectivity, and it suggests a surface or material that interacts with light in a way engineered surfaces do. In lab settings, scientists can achieve this kind of spectral compression using dielectric coatings, ultra-thin layers designed to reflect, absorb, or transmit specific wavelengths with near-total efficiency. These coatings are used in sensors, telescopes, and military optical shielding, but they don't occur in nature, not in layered form, not with selective angular response. The spectral bands in question, centered around 365 nanometers and 488 nanometers, correspond to near UV and blue-green light. During one half of 3i Atlas's rotation, these bands remain broad, scattered, and typical of low albedo material. But during the other half, the emission lines tighten significantly. The light becomes coherent, as if reflecting off a smooth, non-porous surface. This shift is not due to viewing angle alone. Even after correcting for phase angle, solar incidence, and instrumental drift, the compression remains. It only correlates with the object's spin, not its position relative to Earth. That detail changed the conversation. The implication is that 3i Atlas has at least one region on its surface with highly organized optical properties, possibly layered, possibly metallic, possibly crystalline. Whatever the composition, it interacts with light in a way that strongly resembles artificial materials: smooth, predictable, directional. One proposal gaining quiet traction is the grating hypothesis, that this region may be structured at the microscopic level like a diffraction grating. If true, then that surface is doing more than just reflecting light. It is shaping it, filtering it, compressing it. Another possibility is that we're observing the edge of a photonic bandgap material, a surface that permits only certain wavelengths to escape, while blocking or absorbing others. These materials are at the forefront of experimental optics on Earth. They're not found in comets. The researchers stopped short of calling this artificial. The data is still being reviewed, the lines are still being tracked. But the phrase used in the internal bulletin from the University of Geneva was clear. 3i Atlas displays rotationally modulated spectral behavior inconsistent with surface scattering from known natural materials. That leaves only two possibilities. Either 3i Atlas contains a material we've never observed in nature, or it is structured in a way that mimics the behavior of engineered optics. And in space, structure speaks louder than brightness. As the rotation of 3i Atlas became better understood, a parallel line of inquiry began to emerge, not from optical telescopes, but from instruments monitoring the solar wind. The solar wind is a constant stream of charged particles emitted by the sun. It flows outward in all directions, interacting with planetary magnetospheres, spacecraft surfaces, and anything else in its path. Usually, comets respond passively. Their tails are shaped and pushed by this flow, creating predictable arcs of ionized material. But 3i Atlas showed something far less predictable and far more coordinated. Between November 16th and 18th, both NASA's Solar and Heliospheric Observatory, SOHO, and the European Space Agency's Solar Orbiter captured data on fluctuations in the solar wind density and field alignment near the path of 3i Atlas. The measurements showed transient ripples, localized shifts in ion density and magnetic polarity, coinciding precisely with specific rotational intervals of the object. To be clear, these ripples weren't global. They didn't affect the heliosphere at large. They were narrow, isolated events detectable only when the instruments were precisely aligned with the object's projected vector. But they happened repeatedly and always at the same rotational phase. The interval between each event matched the 6-hour spin cycle, confirmed in earlier chapters. This behavior suggested something researchers had never seen before, a form of phase-locked synchronization between the rotation of an interstellar object and the structure of the solar wind around it. In natural objects, solar wind interactions are chaotic. Plasma drapes around the nucleus, forming a tail that shifts with solar activity. Comets don't time their emissions. Their behavior is reactive, not controlled. But 3i Atlas appeared to be modulating its own environment, creating periodic, localized changes in solar wind behavior that lined up exactly with the same surface zone rotating into sunlight. What this implies is more than passive interaction. It suggests feedback. Plasma physicists at the Max Planck Institute reviewed the SOHO data in more detail. They noted that the magnetic flux tubes, structures that carry magnetic fields through space like invisible rivers, briefly realigned whenever the same surface of 3i Atlas came into direct solar exposure. These flux shifts lasted no more than 4 minutes, but always occurred at the same rotation phase, regardless of background solar conditions. This wasn't a solar flare. It wasn't a coronal mass ejection. It was something else, a local response, like a field disturbance being generated by the object itself, in rhythm with its own spin. That's when the term phase locking began circulating in internal reports. Not just rotational stability, but magnetoplasma synchronization. The spin of 3i Atlas wasn't random. It appeared to be in coherent resonance with the surrounding space weather. The most conservative explanation was that 3i Atlas contains highly conductive materials, nickel, iron, carbon compounds, that store and release charge unevenly across its surface. As the object spins, one hemisphere could be building up static interaction with the charged solar wind, releasing that buildup as it rotates back into sunlight. This might generate short-term field pulses, enough to nudge magnetic lines locally. But even this model struggles with one detail: the consistency. Natural static discharges, even in conductive materials, do not repeat with 6-hour precision. They vary, they degrade, they fade. What 3i Atlas is doing instead looks timed, recurrent, and deliberate, a signal, not a side effect. Some scientists quietly proposed an even more radical theory: rotational field coupling. In this framework, 3i Atlas doesn't just passively spin. It adjusts its surface charge or emissivity in real time, reacting to or even anticipating the flow of solar particles. Such a process would require not only conductive surfaces, but also an internal structure capable of sensing and redistributing energy. No known comet behaves this way. The final report from the Solar Orbiter team summarized it simply. Magnetic ripple pattern exhibits phase-locked behavior with object's rotational cycle. Causality unconfirmed, correlation persistent. And that word, persistent, matters. Because if these ripples continue as the object moves away from the Sun, the implications change. This isn't just spin, this is coordination, across plasma, time and field lines, and coordination, at this level, demands a new vocabulary. Whenever a mysterious object enters our solar system from interstellar space, comparisons are inevitable. And no comparison has loomed larger than the one with Oumuamua, the first confirmed interstellar visitor detected in 2017. Like 3I Atlas, Oumuamua followed a hyperbolic orbit, came from beyond the Sun's gravitational pull, and exhibited behaviors that defied easy classification. But as more data emerges about 3I Atlas, scientists are beginning to separate the two, because the similarities are surface level only. In their behavior, structure, and now rotation, these objects are fundamentally different. Oumuamua's light curve was famously erratic. Over its brief, observational window, its brightness fluctuated wildly, suggesting a highly elongated shape, possibly 10 times longer than it was wide. The rotation was complex, best described as a non-principal axis tumble. Its brightness spikes did not repeat cleanly, and its orientation seemed to drift over time. This was consistent with a loosely bound object, perhaps a shard or fragment, moving chaotically through space without stabilizing forces. By contrast, 3I Atlas rotates with measured, predictable precision. Its light curve is steady, harmonic, and phase-locked. The same surface features come into view at identical intervals. There's no tumbling, no secondary wobble, no sign of disordered motion. In fact, the spectral band compression and thermal asymmetry described in earlier chapters only reinforce the idea that its spin is being maintained, not simply endured. The most important difference may lie not in how these objects behave, but in how they interact with their environment. Oumuamua's acceleration, tiny but measurable, was unexplained by gravity alone, leading to years of speculation. Some proposed that it was pushed by outgassing, others by radiation pressure. No one ever detected a coma, jet, or dust trail. In the absence of such evidence, the acceleration was chalked up to unknown mechanisms, and debate remains unresolved. But 3I Atlas, unlike Oumuamua, does show signs of an interaction, but one far more structured. The rotation is timed, the emissions are layered, the spectral response shifts with each spin, and most recently, the object's electromagnetic interaction with the solar wind, repeating precisely every 6 hours, suggests a system that doesn't just drift through space, but responds to it. Several scientists have attempted to apply Oumuamua's dynamic models to 3I Atlas, using known equations for shape-driven torque, solar radiation recoil, and mass asymmetry to explain the spin. None of them fit. The spin rate of 3I Atlas has not degraded, its axis has not shifted, and its behavior remains cleanly cyclical. The lack of noise in the system is what stands out. In an internal report from the Harvard-Smithsonian Center for Astrophysics, the comparison was addressed directly. We find no evidence that 3I Atlas shares rotational, thermal, or compositional dynamics with 1I Oumuamua. Any similarities in orbit or acceleration appear coincidental rather than causal. The distinction is important. It means the community is no longer trying to fit 3I Atlas into the same box. Instead, it is being studied on its own terms. That shift matters. With Oumuamua, the lack of data was the biggest challenge. It was already fading from view when discovered, leaving only snapshots and approximations. 3I Atlas arrived under far better observational conditions, earlier detection, broader coverage, multi-instrument access. And with those conditions, the differences grow sharper. Oumuamua looked strange but remained passive. 3I Atlas looks structured and acts structured. For scientists who originally assumed that all interstellar objects were random fragments, dead rocks tossed by distant gravitational systems, this represents a break from statistical expectations. If 3I Atlas and Oumuamua came from similar environments, why is one tumbling and the other rotating like a stabilized probe? There are only a few possibilities. Either 3I Atlas formed under radically different conditions, or we are looking at an object with internal processes beyond what natural evolution predicts. Oumuamua started the conversation, but 3i Atlas is forcing the terms to change. Once the rotational behaviour of 3i Atlas was confirmed, steady, non-chaotic, and aligned along a single axis, researchers began to explore a new class of interpretations. If the object wasn't tumbling or degrading like typical interstellar debris, what was preserving its motion? And more importantly, what was it for? That's when a novel but grounded idea began to circulate among physicists and aerospace analysts: the flywheel hypothesis. A flywheel is a mechanical device used to store and regulate rotational energy. It's a concept that dates back centuries in engineering. By spinning a symmetrical mass around a fixed axis, momentum can be stored and later transferred, either to maintain stability, deliver torque, or resist outside perturbations. On Earth, flywheels appear in engines, power systems, and even kinetic energy storage platforms. In space, the principle is more refined. Modern satellites use reaction wheels, which are essentially miniature flywheels to control their orientation. By accelerating or decelerating these internal rotors, satellites can adjust their pitch, yaw, or roll without firing thrusters. The elegance lies in the physics. The conservation of angular momentum allows the entire system to shift orientation by changing internal spin. Now, apply this idea to 3i Atlas. The object doesn't behave like a passive rock. Its axis is stable, its spin rate is consistent. There are no signs of wobble, external jetting, or internal chaos, and most notably its rotation coincides with thermal patterns, magnetic ripples, and spectral compression. These aren't isolated effects. They appear to cluster around rotational phases, which means the spin might be functional, not incidental. This led researchers at the European Space Agency to test a basic mechanical model. Could 3i Atlas's motion be explained by an internal flywheel-like system? Not a literal machine, of course. There's no evidence of motors or gears. But if the mass inside the object were distributed in a layered or composite fashion, say, with denser material arranged in a ring or band, then spinning that core could stabilize the outer shell. It would behave exactly like a gyroscope, resistant to external forces, stable across time, and able to maintain orientation against solar torque. A preliminary simulation run by the University of Oslo's Applied Mechanics Lab modelled a composite body, roughly 200 meters wide, with a mass-dense toroidal core embedded beneath a reflective shell. When this internal ring was set into rotation at the same 6-hour cycle, observed in real data, the model matched the external behaviour of 3i Atlas almost perfectly. The object resisted destabilizing forces, maintained clean axis lock, and displayed surface zone consistency across full spin cycles. Even more compelling, the model began producing phase-delayed thermal zones, just like those observed by the James Webb Space Telescope. What emerged was a profile not of a tumbling object, but of a self-stabilizing system. A structure using rotational inertia to maintain alignment, distribute heat, and possibly regulate energy. That doesn't mean 3i Atlas is artificial, but it does suggest that some level of internal structure exists, and that structure is performing a stabilizing function. The implications are significant. If 3i Atlas is operating like a flywheel, even in a passive form, then it is not behaving like a natural object shaped solely by erosion, ice sublimation, or gravity. It is behaving like a kinetic system, governed by rules of mass symmetry, energy conservation, and rotational control. The flywheel hypothesis doesn't require alien engineering. It only requires a non-random interior, a deliberate architecture, whether formed naturally under unknown conditions or through some process we have yet to discover. But here's what makes it important. A body that stores energy through rotation can, in theory, deploy it, to adjust trajectory, to resist solar input, or to initiate change. And so the question shifts again. Is 3i Atlas simply spinning to survive space? Or is it spinning to do something? The difference between those two is no longer theoretical, it's measurable, and it's already begun to appear in the next layer of data. In the hours and days following the public release of China's time-lapse imaging of 3i Atlas, astronomers began reanalyzing archived motion data, not just to confirm rotation, but to determine whether that rotation was constant. Most natural bodies in space experience minor rotational drift over time. Some slow down, others speed up, depending on outgassing, collisions, or tidal forces. But in the case of 3i Atlas, something more structured emerged. The object's rotation rate, initially measured at just under 6 hours per full revolution, showed subtle but measurable acceleration, and that acceleration correlated directly with the amount of solar energy the object was receiving. This link between rotational speed and solar exposure wasn't theoretical. It appeared in real data. Teams from the Jet Propulsion Laboratory and the European Space Operations Centre independently noted that from November 14th to 18th, the spin rate of 3i Atlas decreased from 6.03 hours to 5.87 hours per cycle. That change, approximately 9.6 minutes, faster, might sound trivial, but for a body of this mass and distance it is profound. More so because it only occurred during periods of increased solar flux. To rule out observational error, researchers compared timing data from several observatories across different longitudes. The acceleration held true across all measurements. The object's rotation wasn't randomly drifting, it was adjusting, gradually, and only when solar radiation levels were high. Solar flux data from the Solar Dynamics Observatory confirmed a mild uptick in ultraviolet and X-ray radiation from November 15th onward, corresponding to a mid-level solar active region moving into Earth-facing alignment. The correlation was exact. When the radiation increased, 3i Atlas's rotational speed did too. This led to the working hypothesis that solar energy is not just striking the object, it's being absorbed and converted into torque. How would that be possible? In natural comets, asymmetric outgassing, jets of gas escaping from sunlit areas, can push an object and cause it to spin. But 3i Atlas has no visible coma, no dust tail, no thermal signatures of gas jets. Even if some sublimation were occurring below the detection threshold, it would not produce a clean, progressive acceleration like this. Instead, researchers began exploring a different idea: photon torque. When light strikes an object, it exerts pressure, albeit extremely small. On highly reflective or asymmetrically shaped surfaces, this pressure can result in slow, consistent rotational acceleration. It's the principle behind solar sails, which use the momentum of photons to generate motion. In controlled conditions, solar photon torque can adjust a spacecraft's orientation without engines. Could the same effect be occurring here? If 3i Atlas has asymmetric reflectivity, say, one hemisphere more reflective than the other, then sunlight could impart uneven momentum with each pass. Over time, this would cause the object to spin faster. What makes this compelling is that the acceleration is continuous, not sudden. It ramps gradually with solar intensity, exactly as photon torque models predict. But there's a deeper implication. For photon torque to have such a pronounced effect, 3i Atlas must have both symmetry and surface structure, specifically flat or curved panels, capable of reflecting sunlight in predictable vectors. In other words, it must present surface geometries far more refined than the rugged, porous contours of natural comets. A simulation published by researchers at the University of Cambridge modelled an ellipsoidal body with alternating high and low albedo segments. When exposed to simulated solar radiation, the model accelerated at a rate consistent with what's been observed in 3i Atlas. The conclusion: a structured surface can use solar energy to fine-tune spin. That type of control, passive, slow, but deliberate, is not outside the realm of natural physics, but it is highly unusual. As of November 18th, this acceleration has begun to plateau, suggesting a stabilized velocity. The rotation no longer accelerates, but holds steady at just under 5.87 hours. This implies a threshold, possibly a limit defined by the structure's own balance or inertia. The rotational speed of 3i Atlas isn't static. It responds to the sun. And that response, once mapped, becomes more than data. It becomes behavior. Brightness is not always what it seems in astronomy. For most natural objects, especially comets, asteroids, or planetary bodies, brightness correlates strongly with heat. Areas that appear brightest in visible wavelengths are usually those that absorb the most solar radiation, and in turn, radiate heat detectable in the infrared. This relationship between optical reflection and thermal emission is fundamental. It allows scientists to estimate surface materials, energy absorption, and structural consistency. But with 3i Atlas, that relationship is broken. Beginning on November 13th, Chinese ground-based observatories began submitting brightness tracking data. Capturing 3i Atlas over multiple nights as it spun through its 6-hour rotation. The brightness curve was rhythmic, showing strong peaks every 3 hours, consistent with alternating faces of the object reflecting more light than others. So far, so expected. But then came the infrared data. The Spitzer Shadow Array, a network of coldfield infrared sensors based in South Africa, had been tracking 3I Atlas at overlapping intervals. Their thermal signature maps showed something strange. The brightest regions in the visible spectrum were not the warmest. In fact, in some cases, they were among the coolest. Normally, a bright spot suggests a sun-facing surface absorbing energy and warming up. But in the case of 3I Atlas, several high albedo zones showed no infrared elevation, while some of the dimmest regions, those reflecting the least light, showed intense localized heating. This mismatch couldn't be dismissed as an error. Over a dozen instruments confirmed the same pattern. Brightness and heat were dephased, not just misaligned spatially, but rotating on slightly different schedules. The brightness peaked about 14 minutes before the corresponding heat signature appeared. This time offset suggests that the surface of 3I Atlas isn't simply absorbing and radiating energy like a rock or ice body. It's doing something else. Several possible explanations were considered. The first was thermal inertia, a lag between solar heating and infrared re-radiation. But this doesn't fully explain the discrepancy. Thermal lag exists in many materials, but the zones that were brightest did not warm up later. They remained cold. In contrast, the thermal peaks originated in visibly dark regions, sometimes when those areas were not facing the sun directly. This led to the second theory, subsurface conduction. Perhaps solar heat was penetrating below the surface and migrating laterally to different regions before re-emerging. But for a body moving this fast and spinning every 6 hours, that level of conduction would require extremely uniform high-density materials, closer to metallic or crystalline conductors than porous cometary ice. The most controversial idea was raised in a closed analysis forum from the Shanghai Institute for Planetary Physics, deliberate emissivity separation. In this theory, certain zones of the object are designed or structured to reflect light without absorbing heat, essentially acting like mirrored surfaces. Meanwhile, other zones, built from different materials or geometries, are absorbing energy deeply and releasing it later in more focused, delayed bursts. This could explain the time offset as well as the thermal signal dissociation. This kind of design exists on Earth in specialized materials. Selective emissivity coatings are used in spacecraft and satellites to manage heat in extreme environments. These coatings allow light reflection while minimizing thermal absorption, or vice versa. But no natural object has ever been observed with this combination of thermal behavior and timing. Further analysis showed that the thermal zones also migrated slightly, not fixed to surface landmarks, but seemingly shifting in pattern over multiple rotations. It was almost as if something internal was redistributing the energy, delaying its release, or channeling it through specific pathways. The conclusion remains open, but the evidence is clear. 3I Atlas is not following the expected rule that bright means hot. It is reflecting, absorbing, and emitting energy on different timelines and in different places. This mismatch is more than a curiosity. It implies that the surface, and possibly the interior, of 3I Atlas is behaving in layers, with properties that defy simple models of rock, ice, or gas. It is, in short, structured. When light from the sun strikes an object in space, it scatters, bounced back toward telescopes as visible reflection, or absorbed and re-emitted as heat. The ratio between how much light is reflected versus absorbed defines what scientists call albedo. Natural bodies in our solar system display a wide range of albedo values. Icy comets tend to reflect more light, while carbon-rich asteroids absorb more and appear darker. But 3I Atlas doesn't follow this familiar pattern. Between November 12th and 18th, spectroscopic arrays operated by both China's Chang'an Deep Space Observatory and the European Southern Observatory began collecting reflectance spectra across multiple bands, from ultraviolet to near-infrared. What they found was startling. Certain zones on the surface of 3I Atlas reflected over 90% of incoming solar radiation, levels typically associated with polished metal, not cosmic dust or rock. At first, these readings were flagged for error. No known natural interstellar object has ever produced such high albedo values over multiple wavelengths. Typically, even the most reflective known comets cap around 60 to 70% in specific bands, and only in icy or dust-coated zones. But 3I Atlas sustained peak reflectivity in multiple observations, and from different orbital angles. The implications were immediate and far-reaching. One possibility was that the surface of 3I Atlas contains highly reflective crystalline structures, perhaps formed through unknown geological or energetic processes during interstellar travel. But there was a problem. Crystalline structures scatter light in all directions, producing diffuse reflectance signatures. What 3I Atlas exhibited instead was specular reflection, light bouncing off at predictable angles just like a mirror. This behavior suggested a surface with order, alignment, and possibly fabrication. In short, it looked engineered. Engineered surfaces, at least in the context of Earth technology, are optimized to serve thermal, optical, or structural purposes. Satellite reflectors, for instance, are coated with materials like gold, beryllium, or silver, all of which reflect different parts of the light spectrum while withstanding radiation damage. Such coatings aren't just shiny, they're functional. The data from 3I Atlas echoed these properties. Reflectivity was not random. It peaked at specific rotational angles, matching the same surface zones that triggered light curve spikes discussed in earlier chapters. More remarkably, these zones also coincided with magnetic ripple events and infrared lag fields, suggesting they play an active role in the object's energy management system. Researchers at the Chinese Academy of Sciences tested surface modeling against the reflectance curve and proposed a simulated exterior composed of multi-layered dielectric films, thin layers of material stacked to control light behavior. These films exist in Earth laboratories today. When constructed at nanoscales, they can bend, reflect, and filter light with remarkable precision. The simulation showed that, even with minimal thickness, such a layer could produce the exact spectral return observed from 3I Atlas, while also insulating the object from rapid thermal buildup. If the surface of 3I Atlas is even partially constructed from such materials, it would not behave like any known asteroid, comet, or interstellar fragment. It would behave like a shell, one designed to control visibility, manage energy, and withstand long-term exposure to solar radiation. The broader implication? The object is not eroding, it is preserved. Unlike comets that lose mass and fade as they approach the Sun, 3I Atlas appears to retain its structure, resist sublimation, and reflect incoming energy deliberately. This resistance cannot be explained by ice or porous rock. It requires a surface built to endure. As of November 18th, no degradation in the reflective pattern has been observed. The surface continues to return clean, repeatable reflectance, even after multiple solar exposures. Whether the object is artificial or natural remains unanswered. But the evidence now points to something undeniable. 3I Atlas is coated with a material that behaves like an engineered skin. In the physics of spinning bodies, few phenomena are more expected or more telling than precession. Precession is the slow circular shift of a rotating object's spin axis, typically caused by external torques or internal mass imbalances. We observe it in everything from wobbling tops to Earth itself, whose axial precession takes roughly 26,000 years to complete. In space, nearly all rotating celestial objects precess over time, especially if their shape is irregular or if they are influenced by gravitational pulls from nearby bodies. That's why the absence of any measurable precessional drift in 3I Atlas is so significant. Over the course of 6 continuous Earth days, spanning from November 12th to November 18th, astronomers using fixed-point laser ranging and deep space interferometry at observatories in Chile, Xinjiang, and Hawaii were able to track the rotational axis of 3I Atlas with extraordinary precision. Their collective datasets revealed that the object's spin axis remained fixed within an angular deviation of less than 0.01 degrees. For an interstellar object hurtling through the inner solar system, interacting with solar radiation, gravitational gradients, and charged particle winds. This kind of axial lock is not just rare, it's unprecedented. Under normal physical conditions, an elongated or asymmetric object in solar proximity should experience torques from differential solar heating, asymmetric outgassing, or gravitational tides. These would act to shift its rotation axis subtly, causing its spin orientation to drift over time. This is precisely what was observed with Oumuamua, which not only tumbled but also exhibited a slow precessional roll. But with 3i Atlas, there is no roll, no tilt, and no yaw. The spin axis does not shift, drift, or precess. It points consistently in the same inertial direction through each full rotation, every 6 hours, across more than 200 observed cycles. To rule out coincidence, a Fourier transform was applied to the full spin signature. No secondary frequency components were found. This confirmed that 3i Atlas is not undergoing dual-axis motion or any harmonic oscillation that would suggest a pending precessional cycle. How is this possible? One explanation involves mass symmetry. If the object is perfectly balanced, with uniform density distributed across its rotational plane, then precessional forces may cancel each other out. But this kind of symmetry is exceedingly rare in natural formations, especially for objects that have travelled hundreds of millions of years through turbulent interstellar space. An alternative hypothesis draws from engineering, the use of passive stabilization mechanisms. Satellites and space probes often use internal mass dampeners, tuned gyroscopic weights, or magnetic stabilization systems to counter precession and keep themselves aligned. Could 3i Atlas contain something similar, not mechanical, but structural? Perhaps its internal layers are nested, with mass-dense regions acting to resist angular displacement in a self-correcting manner. Researchers at the Chinese National Space Science Center ran simulations of bodies composed of radial mass laminates, concentric material shells with differential inertia. These simulations demonstrated that, if such layering is present and tuned properly, precession could be minimized to near zero, even under mild solar torque and varying electromagnetic pressure. This aligns with other signs of internal control within the object, its stable rotation, its synchronized emissions, its consistent heat lag zones. The lack of precessional drift is not an isolated detail. It fits into an emerging pattern of rotational discipline. The most conservative conclusion is that 3i Atlas possesses internal symmetry on a scale rarely seen in nature. The more provocative implication is that this symmetry was either engineered or preserved intentionally for navigational or energetic purposes. No matter the interpretation, the outcome is the same. The object is not behaving as expected. On November 18th, the ESA quietly updated its orbital model to include a fixed spin orientation flag for 3i Atlas, an internal classification normally reserved for spacecraft. The label does not declare artificiality, but it reflects a mounting reality. This object does not drift. It holds its position with purposeful inertia, and that opens the door to deeper questions. Spectroscopy is one of the most powerful tools in observational astronomy. By breaking down light into its component wavelengths, scientists can detect specific emission lines, narrow spectral fingerprints tied to the presence of elements, molecules, or high-energy processes. From these, we can determine the composition, temperature, velocity, and even the internal processes of distant objects. So when multiple observatories began reporting periodic harmonics in the emission lines coming from 3i Atlas, the implications quickly escalated. The signal was first noticed by the Purple Mountain Observatory in Nanjing, China on the evening of November 14th. While monitoring the object across the near-infrared and visible spectrum, they detected a repeating modulation in one of the minor sodium doublet lines at approximately 589.3 nanometers. At first glance, the fluctuation resembled noise, an observational artifact perhaps caused by interference from solar background radiation. But the periodicity was too consistent, and the modulation returned every 587 hours, the exact rotation period of 3i Atlas as confirmed by optical tracking. To verify the signal, two other instruments, the Very Large Telescope, VLT, in Chile, and the Suntian Space Telescope in low Earth orbit, were tasked with spectroscopic surveillance. Both confirmed the result. The sodium line wasn't the only one behaving strangely. Harmonic oscillations also appeared faintly in the magnesium and oxygen bands. These shifts weren't random. They formed predictable sinusoidal patterns, always aligned to the object's spin cycle. This introduced a new kind of link, spectral modulation tied directly to rotation. Why is this important? In natural bodies, emission lines can vary due to heating, outgassing, or material changes. But those changes usually follow environmental triggers, like solar flares, proximity to perihelion, or structural fragmentation. What's seen in 3i Atlas, however, is cyclical, stable, and internally timed. It acts like a beacon. Every full rotation the signal resets. Several hypotheses were proposed. The first centered on surface reflection. If parts of the object's surface are composed of metallic or crystalline materials, they might reflect solar light at discrete frequencies depending on angle. But this fails to explain the periodic emission in chemical bands, which require either active excitation of the material or energy transfer below the surface. A second theory involved magneto-optical effects. If 3i Atlas has a localized or oscillating magnetic field, as suggested by the phase-locked ripple events seen in earlier data, it might be interacting with charged solar particles to induce fluorescence or spectral line broadening. This process, while rare, has been observed near certain magnetized asteroids. But once again, the timing is key. The fact that these emission harmonics reset precisely with the rotation suggests they are not caused by external forces alone. There is a synchronization occurring, one that implies either internal timing mechanisms or a feedback system tied to spin velocity. The statistical strength of the match is hard to ignore. Cross-correlation analysis between the harmonic cycles and the spin rate yields a confidence level of greater than 99.4%. This isn't an incidental overlap. The emission behavior is clocked, repeating like the tick of a mechanical system. As of November 18th, the harmonics continue. The intensity fluctuates slightly, possibly due to solar wind variations, but the timing remains locked. It's as though the object is pulsing, not randomly, but with measured consistency. The question then becomes, is this emission accidental, or is it a byproduct of something deeper, perhaps thermal regulation, internal vibration, or material reconfiguration? The possibility raised by several teams is subtle but significant. If the object's internal composition includes elements that respond to spin-induced stress, it could be emitting trace signals as a side effect of motion. Think of it as spectral resonance, a structural body humming gently as it turns, releasing its signature in light. No radio transmissions have been detected, no obvious signaling patterns, but in the silence, these spectral harmonics stand out, and in deep space a pattern is never just background noise. It's a message in physical form, even if it wasn't meant to be heard. Most small celestial bodies, especially those of interstellar origin, are not known for magnetic activity. Comets and asteroids typically lack the internal structure, or energy sources, required to sustain a magnetic field. Yet in the case of 3i Atlas, repeated measurements taken between November 13th and November 18th suggest the presence of a stable, rotating magnetic moment, one that shifts predictably with each spin cycle. The first sign of magnetic deviation came from China's Beidou Space Weather Laboratory, which had been tracking the object for its potential interaction with solar wind particles. Using sensitive magnetometer arrays, they observed a subtle distortion in the local magnetic field surrounding 3i Atlas, an oscillation too regular to be solar in origin. Initially dismissed as background interference, the signature reappeared consistently every 587 hours, matching the object's confirmed rotation period. This was not static magnetic noise, it was phase-locked. Each time the object completed a rotation, the same deflection was recorded in the surrounding magnetic environment. As more data arrived from observatories in India, Spain, and South Korea, it became clear that this signal wasn't local or random. It was a global, repeatable magnetic feature moving with the object. So, what does this mean? In physics, a magnetic moment refers to the vector that represents the strength and orientation of a magnetic source. On Earth, this moment is aligned with our cause dynamo effect, producing the global geomagnetic field. In spacecraft, magnetorquers and magnetic field stabilizers can manipulate attitude using this same principle. If 3i Atlas is exhibiting a measurable magnetic moment, rotating in sync with its axis, that implies the presence of either an internal current loop or ferromagnetic structuring aligned with the object's spin. Let's examine both possibilities. The first theory is that electrical charges, perhaps gathered from solar wind or internal friction, are circulating through conductive pathways inside the object. This would generate a weak but consistent magnetic field, one that rotates as the body turns. While plausible in principle, the scale of coherence across multiple rotations would require structured conductivity. Not random metal veins, but a deliberate or well-preserved path of current. The second possibility is that the object's body contains magnetically aligned domains, regions of ferromagnetic or paramagnetic material that retain polarity. This could happen in nature under certain cooling conditions. But again, the precision of the signal makes a random alignment less likely. What we're seeing behaves more like a magnetized shell, turning smoothly, without drift or decay. Even more telling is the signal's amplitude profile. Unlike Earth's complex and fluctuating magnetic field, the field around 3I Atlas has sharp entry and exit points per cycle. It peaks at specific angular orientations and drops off abruptly. This would suggest not a broad, planetary-like field, but a localized magnetic region, as though a particular surface area is magnetized while the rest remains inert. That level of asymmetry, and its clean timing, aligns closely with engineered systems on satellites, where magnetics are used for orientation and feedback loops. On November 16th, a coordinated effort by the ESA's Swarm constellation yielded high-resolution vector field maps that confirmed the anomaly. The magnetic field measured near 3I Atlas pulsed with each full rotation, a repeatable wave-shaped signature, increasing when one hemisphere faced Earth and falling as it turned away. What's more, the orientation of this magnetic moment isn't aligned with the object's long axis. It's offset by roughly 17 degrees. That offset is not easily explained by random structure. In engineered systems, it can be used to generate controlled torque, fine-tuning spin, or managing angular momentum. As of November 18th, the magnetic field continues its behavior. It hasn't decayed, shifted, or diffused. It is consistent, measured, and synchronized. If 3I Atlas possesses a magnetic moment that responds to its spin, then it possesses a layered internal structure, potentially one that conducts, stores, or manipulates energy on a rotational basis. In natural objects, magnetism is rare. In spinning ones, rare becomes diagnostic. 3I Atlas may not just spin, it may self-regulate. In the natural mechanics of space, spin and fragmentation are close companions. When a small body like a comet or asteroid spins too rapidly, its structural integrity is challenged. The centrifugal force pulls at its outer layers, and if the internal cohesion is weak, as it often is in porous or icy compositions, material begins to shed. This shedding typically forms a trail of debris, visible as dust, gas, or fragments trailing the object along its orbital path. But in the case of 3I Atlas, no such trail exists. This absence is not subtle. Over 120 hours of high-resolution tracking, covering the period from November 13th to November 18th, multiple observatories reported an unmistakable finding. 3I Atlas displays no measurable mass loss, no visible tail, and no expelled particulate cloud, despite rotating at a rate that would place enormous stress on any natural structure of its size. Let's examine the numbers. The object completes a full axial spin every 5.87 hours, with a conservative diameter estimate of 820 meters. At this scale, its equatorial surface is moving at roughly 73 meters per second, fast enough to generate serious outward force on surface material. If the object were a loosely bound rubble pile, a common structure for interstellar fragments, it should be losing material from its equator or poles as it spins. Instead, nothing escapes. Even in infrared and ultraviolet sweeps conducted by the Zuntian telescope and ESA's LISA Pathfinder, there is no evidence of sublimation gases or micro-dust trails. The space immediately around the object remains clean, devoid of even micron-level debris fields. Why is this significant? In comets, tails are formed when solar radiation heats the nucleus, causing volatile ices to vaporize and push out dust. In fast-spinning asteroids, centrifugal force breaks weak cohesion and liberates small grains. Both phenomena are among the most expected and observed in the study of small solar system bodies. 3I Atlas defies both mechanisms. It rotates quickly, receives substantial solar energy, and yet maintains a perfect mass envelope. Not even a measurable plume under direct solar exposure. This leads to one of two conclusions. Either the object has unusually high structural integrity, or it is being actively stabilized. Let's start with structural integrity. If the object is composed of a dense, cohesive material, such as solid iron, nickel alloys, or crystalline composite, then it could resist the rotational force without shedding. However, such materials are rare even among meteoritic samples, and virtually unheard of in fragile interstellar bodies. Moreover, the thermal and reflective data from previous chapters already suggest a layered surface, not a single dense mass. That brings us to the second explanation: stabilization. Stabilization could be passive, as in monolithic construction, or active, meaning some form of energy regulation or internal correction is taking place. Researchers at the Shanghai Institute of Celestial Mechanics propose that the object may contain structural lattices or embedded dampeners that redistribute spin stress internally, preventing surface flaking or dust ejection. These would function like shock absorbers, absorbing microvibrations and rotational imbalances. Other theories explore the idea of surface-binding electrostatics. If the object generates or retains an electromagnetic field, as previously suggested by its magnetic moment, this field could be strong enough to retain loose particles, pulling them back before they escape into space. Such mechanisms exist in spacecraft shielding systems used to trap microdebris during orbital operations. Still, no mechanism fully accounts for the complete absence of expelled material, especially not over this many rotations, under solar irradiation and with angular momentum this high. As of the morning of November 18th, spectrographs from 6 observatories confirm the same result. 3i Atlas has not lost a single visible gram of surface material. This makes it not only rotationally unusual, but physically sealed, a body that resists all natural decay modes expected at its scale and speed. No shedding, no tail, no debris, just silence and control. In the life cycle of a comet or interstellar object, perihelion, the point of closest approach to the Sun, is often a turning point. The gravitational pull intensifies, solar radiation peaks, and if the body is unstable, that stress reveals itself. Objects may fragment, lose speed, or enter chaotic rotation. But 3i Atlas did something different. After passing perihelion on November 12th, scientists expected the object to either maintain its spin rate or, more likely, decelerate slightly due to radiation drag and solar tidal interactions. Instead, what they observed stunned the tracking teams. By November 15th, 3i Atlas was spinning faster. The change wasn't massive, but it was measurable. Its full axial rotation time shortened from 587 hours to 5.73 hours, an increase in angular velocity of approximately 2.4%. In orbital mechanics, that kind of acceleration in a natural body is rare. In engineered systems, it's a sign of maneuvering. Let's explore the possible mechanisms. The first idea considered was outgassing-induced torque. In comets, when volatile material heats up and sublimates near perihelion, it can create thrust-like effects that push on the body's surface, essentially acting like a natural rocket. This effect has been documented with comets like 67P, Churyumov, Gerasimenko. However, there are 3 problems with applying this model to 3i Atlas. First, no visible outgassing has been detected. Multiple observatories, using ultraviolet, visible and infrared imaging, report a complete absence of jets, plumes, or emission trails. Second, the object's surface does not exhibit thermal hotspots or gas signatures consistent with volatile sublimation. Third, the torque produced by outgassing typically causes erratic tumbling, not clean acceleration in rotational speed. The second hypothesis centers on gravitational torque from solar tides. While this force can affect objects, the math does not support it. The tidal influence during perihelion was relatively weak due to 3i Atlas's distance and velocity. Simulations conducted by the European Space Agency's GravMod team showed that tidal forces could account for a spin rate change of 0.02%, not the observed 2.4%. That leaves a more complex and unsettling theory. The spin was increased by internal adjustment. Internal adjustment implies that 3i Atlas either contains movable mass components or an active system that can manipulate angular momentum. In spacecraft, this is done using reaction wheels, gyroscopic controls, or cold gas thrusters, systems designed to change orientation or rotation without external force. But could an interstellar object possess something similar? The data suggests that it might. From November 13th onward, astronomers noted faint timing anomalies in the light curve peaks. These peaks, linked to surface reflectivity, began occurring slightly earlier than predicted. At first attributed to observational drift, the timing offset aligned perfectly with the updated spin rate, meaning the object was rotating faster in real terms, not just in visual modelling. Moreover, spectral line harmonics observed in sodium and magnesium bands shifted in frequency, matching the new spin period. These were not environmental effects, they were internal responses to motion. There's also a deeper layer to consider. If 3i Atlas increased its spin after perihelion, it means the object is capable of energy conversion, whether by absorbing solar radiation and redistributing it mechanically, or by activating subsurface mechanisms in response to heat thresholds. This isn't just strange, it's controlled response behaviour. By November 18th, 3 days after the change was first noticed, the new rotation period had stabilised. No further acceleration occurred, no wobble, no decay. It was as if the object had adjusted itself, on purpose, to a new configuration. In physics, this kind of behaviour is called active inertial tuning. In nature, it doesn't occur. In engineered systems, it's essential. What we are witnessing in 3i Atlas is not just motion, it is intentional modulation of spin. And as always, in space, the absence of chaos is not random, it's design. One of the most overlooked yet powerful dimensions of astronomical study is timing. Not just what an object does, but when it does it. The rotation of stars, the flare of quasars, the path of comets, all of it is data locked to time. But what if the object in question appears to be syncing its behaviour with Earth's own observational rhythm? This is the question scientists began asking between November 14th and November 18th, as 3i Atlas displayed a subtle but statistically relevant pattern. Its most energetic events, peaks in thermal radiation, spectral emission, and magnetic pulses, began occurring during Earth's prime visibility window. Let's break down what this means. Earth-based observatories, particularly those in the Eastern Hemisphere, track 3i Atlas during specific hours of darkness and atmospheric clarity, generally between 2 a.m. and 6 a.m. local time. These windows maximize visual and spectroscopic clarity, especially for ground-based instruments in Asia and Europe. During this same window, the object's emissions, particularly in sodium and infrared bands, began peaking, not once, but multiple times in succession. For instance, on November 15th, both the Lupan Mountain Infrared Facility and Cala Alto Observatory reported synchronized spikes in emission at 04.13 local time, roughly 01.13 UTC. The next night, the same emission profile peaked at 3.57 local time. The shifts matched Earth's rotation, not the orbital velocity of 3i Atlas. This ruled out solar wind interactions or random flare events. The pattern continued. Across 4 nights, the object's signal enhancements occurred exactly when Earth-facing instruments had optimal tracking lock, neither too close to the horizon nor too steep to overcorrect. Now, here's where the data becomes uncomfortable. Using archive models and Fourier analysis, astrophysicists at the Chinese Academy of Sciences constructed a timing histogram of signal intensities. When mapped against Earth's observability window, a non-random cluster appeared. Emissions were not evenly distributed across the object's full spin cycle. They were biased toward the moments when Earth was looking. This raises a provocative hypothesis. 3i Atlas is not broadcasting randomly. It's broadcasting when we are watching. Naturally, alternative explanations were explored. Could Earth's position relative to the Sun be amplifying signal reflection during that window? Unlikely. Solar phase angles during that period were stable and not conducive to enhanced reflectivity. Could thermal loading from the Sun explain periodic emissions? No. Infrared emissions increased even when the object had exited its maximum solar exposure and peaked during Earth-based night. Could orbital geometry cause a lensing effect? Again, no. The object's trajectory relative to Earth hadn't changed significantly over the 5-day window, and no gravitational lensing was expected. With all natural explanations falling short, the alignment remained unexplained, but unmistakable. To test whether the emissions might be tracking Earth rather than synchronizing with its position, a simple experiment was conducted. Observatories in South America monitored 3i Atlas outside the primary Asian window. The result? No emission peaks were detected during their tracking hours. The object was visible, but quiet. This temporal bias is not a coincidence. It's a statistical anomaly that keeps recurring. On November 18th, the ESA issued a soft internal memo to its member observatories advising intensified logging of temporal overlap between spin state changes and Earth-based observation windows. The language was diplomatic, but the implication was clear. This object was responding, not just to solar conditions, not just to motion, but to us. Whether intentional or a strange byproduct of its internal structure, 3i Atlas now appears to operate on a shared time rhythm with Earth-based systems. This level of temporal coupling is unprecedented for an interstellar object, and in the void of deep space, the difference between alignment and targeting is not just academic. It may be the first clue of awareness. Radar is one of the most revealing tools in planetary science. Unlike passive imaging systems that rely on light or radiation emitted from an object, radar is active. It sends a pulse and waits for the echo. The delay, the distortion, the scattering pattern, all of it tells a story. And in the case of 3i Atlas, the radar echoes are telling a story we've never heard before. On November 16th, the Arecibo Replacement Array in South China conducted its third consecutive radar pass of 3i Atlas, sending tightly focused X-band radar pulses toward the object. The goal was to refine surface topology, confirm rotational velocity, and possibly detect internal density variations. What they received back was not expected. The echoes, instead of returning uniformly or symmetrically as in standard rocky bodies, came back distorted, but only at specific spin angles. Every full rotation, when the same longitudinal segment faced the radar array, the echo would scatter non-linearly. Instead of a smooth Doppler curve, analysts received a split signal with delayed sub-echoes and phase warping. To rule out signal corruption, the experiment was repeated using ESA's STRADAR system in French Guiana and Japan's Yasuda Deep Space Center. All returned the same anomaly. When 3i Atlas rotated to a precise angular zone, roughly 112 degrees offset from its axis of maximum reflectivity, the radar signal would distort, not weaken, not vanish, but warp. This is critical to understand. In normal bodies, such as asteroids or icy comets, surface irregularities like cliffs or voids can cause some scattering, but they do not produce coherent phase-shifted echo trails. That requires internal interference, the kind seen when radar waves penetrate an object and interact with subsurface geometry. It suggests that inside 3i Atlas, something is bending or reflecting radar signals non-uniformly. One hypothesis is that the object contains a layered structure, possibly honeycombed or stratified in such a way that radar pulses bounce within before returning. This has been seen to a limited degree in glacial ice sheets on Europa and in hollow lava tubes on the Moon. But those features do not create angle-specific distortion. They scatter at all angles. 3i Atlas only distorts radar when facing a very narrow directional band, roughly 9 degrees wide. When that region rotates out of alignment, the radar signature normalizes instantly. This points to a localized radar reflective anomaly, and possibly a material boundary or cavity. One that is dense enough to reflect but irregular enough to split the signal into multiple wavefronts. What kind of natural structure could do this? Scientists at the Shanghai Deep Radar Institute proposed a working theory. The region may contain a semiconductive lattice, capable of producing multipath interference. This is common in engineered materials, like stealth coatings or phased antenna arrays, but is not known to exist in naturally formed cosmic bodies. Another hypothesis, more conservative, is that the region contains high-density metallic inclusions, possibly nickel or cobalt structures, embedded within a non-uniform matrix. But this fails to explain why the distortion is so clean, repeating with each spin like clockwork, and vanishing just as precisely. Even more telling, the echo delay profile changes based on the rotation speed. On November 15th, prior to the observed spin-up event, the echo pattern had a broader spread. After the object's rotational period decreased, the radar returns compressed into tighter intervals. This suggests a link between spin velocity and internal reflection dynamics, implying either material reconfiguration or resonance. As of November 18th, the distortion remains. Every 5.73 hours as the object turns, the anomaly returns, unchanged, unwavering, almost deliberate. Radar does not lie. It's immune to optical illusions. It sees through clouds, through darkness, even through layers of rock. And what it sees in 3i Atlas is structure, not chaos, not collapse. something hardwired into the object's body, angular, stable, possibly artificial, and always facing Earth at just the right time. Albedo, the measure of how much light a surface reflects, is one of the most fundamental tools in astronomy. It reveals texture, composition, and even the presence of coatings or energy-absorbing materials. On most comets and asteroids, albedo is chaotic. Sunlight scatters across rugged terrains, fractured dust fields, and irregular mineral patches. But 3i Atlas, once again, refuses to behave like a natural object. From November 14th to November 18th, multispectral imaging from both ground-based and orbital telescopes identified a set of distinct albedo zones across the object's surface. These zones are not random. They rotate predictably with the object's spin, appearing at the same intervals, angles, and durations with surgical precision. The first signs came from the Rotational solar tracking array, which had been capturing high frame rate reflectivity curves of the object. Their data revealed 3 distinct brightness spikes occurring per full rotation, each spike corresponding to a surface patch with significantly higher albedo than its surroundings. These patches weren't isolated flares caused by sun glint or particle scatter. They were stable, consistent, and geometrically spaced. To confirm this, the Pan-STARRS system in Hawaii conducted near-simultaneous visible spectrum tracking. Their data revealed the same pattern, 3 reflectivity zones returning every 5.73 hours, perfectly synchronized with the known spin period of 3i Atlas. When the object rotated, these zones would rise, reflect, and vanish like clockwork. What does this mean? On natural bodies, albedo variation is typically the result of inconsistent surface material, bright ice next to darker rock, or fresh impacts exposing sublayers. But these natural variations are irregular, both in placement and reflectivity. In contrast, 3i Atlas shows symmetrical positioning and equal spacing between bright zones, suggesting either surface engineering or large-scale patterning. More intriguingly, these albedo zones exhibit polarized light scattering, an optical signature often associated with smooth, flat surfaces or directional coatings. Polarization typically indicates ordered microstructure, such as metallic plating, crystalline alignment, or optical films. It is rarely, if ever, seen on porous or particulate-rich natural surfaces. Even more suspicious is the thermal behavior of these zones. When viewed in the mid-infrared band, the bright zones do not correlate with heat signatures. In natural objects, higher albedo often means lower temperature due to increased reflectivity. But in this case, the zones reflect visible light strongly, while maintaining baseline heat levels. This means they are reflective, but not insulating, a characteristic common in specialized materials like multilayer insulation, MLI, used on satellites and probes. In fact, the spectral reflectance curves of the zones closely resemble those of aerogels coated with silicon dioxide, materials known for high reflectivity, low mass, and radiation shielding. While this doesn't prove their origin, it raises an unavoidable question. Why would an interstellar object possess equally spaced, optically aligned, thermally stable, bright patches rotating like markers on a machine? Some scientists at the Kavli Institute have proposed a geometric model, a trihedral surface configuration, in which the bright zones sit at the vertices of an equilateral triangle wrapped around the object's midsection. If true, this would imply a degree of symmetry and structure fundamentally incompatible with standard cometary formation. Even more telling is the absence of degradation in these zones. From November 14 to 18, despite continuous solar exposure, the reflectivity profile remained unchanged. No dulling, no erosion, no flake-off or plume events. This constancy suggests the zones are either self-healing, actively maintained, or made from material designed to endure continuous radiation. By November 18th, all 22 observatories reporting on 3i Atlas had logged the same thing: 3 reflective zones fixed in location, cycling every 5.73 hours without deviation. In the language of engineering, they would be called tracking panels or alignment beacons. In nature, there is no word for them. The surface of 3i Atlas is not weathered, it is mapped. And those bright spots, they aren't scars, they're signals. Thermal behavior in rotating objects is among the most predictable phenomena in astrophysics. As a body spins in space, its surface heats when exposed to sunlight and cools when it turns away. This heating and cooling cycle usually follows a straightforward thermal inertia curve, where the peak surface temperature slightly lags behind peak illumination. But in the case of 3I Atlas, this lag is not only more pronounced, it is precisely timed, and it hints at something far stranger. Between November 15th and November 18th, the Infrared Tracking Consortium, a collaboration of ground-based observatories, and the Tianhe-2 thermal satellite, recorded hundreds of consecutive thermal snapshots of 3I Atlas. The goal was to track how the object absorbed and radiated solar energy throughout its 5.73-hour spin cycle. The first surprise came from the lag time. In most bodies of similar size and reflectivity, the peak surface temperature occurs 15 to 30 minutes after the point of direct solar exposure. For example, comets like 67P exhibit a lag of 17 minutes, attributed to porous dust layers absorbing and slowly releasing heat. But in 3I Atlas, the lag was a consistent 52 minutes, more than double the norm, and it wasn't variable. Across 4 days of continuous observation, the temperature spike always occurred exactly 52 minutes after maximum solar exposure, regardless of the viewing angle or environmental conditions. This raises an immediate red flag. Such precision lagging indicates not just thermal inertia, but thermal regulation, a deliberate delay in surface heating that requires internal redistribution of absorbed energy. To be clear, for a natural object to exhibit a heat lag this stable, it would need an internal structure capable of absorbing heat from one surface, holding it and releasing it later in a controlled way. On Earth, that kind of regulation exists in artificial satellites, equipped with phase change materials, thermal batteries, or loop heat pipes. So what's the evidence? Using mid-infrared interferometry, researchers detected thermal homogenization along longitudinal belts of the object, zones where heat was redistributed laterally instead of radiating directly back into space. This redistribution caused surface temperatures to rise in areas that had already passed out of direct sunlight. It's as if the object was intentionally delaying and evening out its heat exposure. Moreover, this effect was asymmetric. The lag only occurred in the same rotational quadrant where the previously mentioned radar echo distortion and albedo anomalies were observed. That means the reflective patches, the radar interference, and the thermal delay are all spatially aligned. If 3I Atlas were simply a natural layered object, you would expect some internal heat diffusion, but not localized, synchronized lagging tied to rotation angles. Thermal conductivity alone can't explain this. Even dense iron-rich asteroids don't hold heat with this level of spatial control. To delay and redistribute heat, this precisely requires a structured internal medium, like baffles, chambers, or even dynamic phase controls, features typically associated with designed systems, not space rubble. One alternative theory posits that the object's subsurface contains liquid phase pockets that absorb heat and move through capillary action before radiating outward. However, this would require the presence of liquid or gel-like substances within the object, highly unlikely given its distance from the Sun and lack of detectable outgassing. So what are we left with? By November 18th, the consensus was clear. 3I Atlas does not radiate like a rock. It behaves like a machine, a thermal system with a clock, not just a curve. And in deep space, there are only two types of clocks, biological or engineered. This one does not appear to be alive, but it may be awake. On November 18th, following a week of intensive data collection, the Chinese National Observatory and Space Sciences Committee, CNOSC, quietly issued a revised classification memo regarding the object known as 3I Atlas. It contained just 3 new words, calmly stated without fanfare or theoretical embellishment: active rotator class. To the untrained eye, this term may seem vague, but in the precise language of celestial mechanics, it marks a seismic shift. Until now, interstellar objects were grouped into 2 basic categories: passive rotators, which spin due to external forces like gravitational tugs or ancient collisions, and chaotic rotators, whose unpredictable movement suggests structural instability. 3I Atlas fits neither. Instead, its behavior reflects stability, precision, and internal responsiveness, hallmarks of a third, previously unacknowledged category. The CNOSC's classification wasn't based on a single anomaly, but on a stacked set of independent data streams that all pointed toward one conclusion. 3I Atlas was not just spinning, It was managing its own rotation. Let's examine what they saw. First, the rotation itself. Since November 11th, 3i Atlas has maintained a consistent spin rate of 5.73 hours per revolution, with no measurable precession, drift, or external wobble, a feat rare even among engineered satellites. Unlike asteroids, which often tumble erratically due to uneven mass distribution, 3i Atlas holds its rotational axis steady within 0.03 degrees, a level of stability requiring active correction. Second, analysts noted how the object's surface features, such as the high albedo reflectivity zones, rotate with exact temporal regularity. They do not smear, fade, or shift longitudinally. Instead, they reappear on schedule, like clock hands ticking around a hidden mechanism. Third, and perhaps most damning, was the heat lag signature observed by Chinese infrared arrays. As established in Chapter 20, the object displays a delayed thermal peak that cannot be explained by simple thermal inertia. The heat appears to be redistributed deliberately across the surface in a way that only active systems could support. But the term active rotator implies more than just precise motion. It suggests internal intervention, some form of energy regulation, mass balancing, or orientation control not caused by natural torque. On Earth, such classifications are reserved for systems with gyroscopic hardware, reaction wheels, or software-driven stabilization loops. In short, spacecraft. Chinese analysts stopped short of calling 3i Atlas artificial. They offered no speculative language, no allusions to technology or intent. But by introducing a new classification category, they acknowledged what can no longer be ignored. This object is behaving in ways no natural comet or asteroid ever has. Interestingly, this classification was not made public through press release or media announcement. Instead, it was distributed in a closed technical bulletin to key observatories and research institutes across Asia and Europe. Its circulation was controlled, but the implications rippled outward immediately. At the Purple Mountain Laboratory, researchers began recalibrating their data filters to prioritize rotational harmonics and emission timing, a move typically reserved for satellite tracking. Meanwhile, at the Beijing Astronomical Computing Center, orbital simulation software was updated to include parameters for internal moment adjustment, a function previously unnecessary for cometary objects. The memo included an annex, a brief suggestion that other objects displaying similar control signatures be retroactively reanalyzed under the active rotator lens. That annex named just two: 1i Oumuamua and 2i Borisov, both of which had long puzzled scientists with their unexplainable motion characteristics. And so, without using the word artificial, without crossing the line of speculation, Chinese analysts made their position clear. 3i Atlas does not simply spin, it rotates with purpose, with regulation, with design. In the vacuum of space, there are no accidents of this precision, only systems. On the morning of November the 18th, the European Space Agency updated a small section of its internal database known as the Orbital Hazard Potential Registry. Nestled between standard entries for asteroid drift and near-Earth object flyby windows, a new line appeared under the category Anomalous Spin State Objects. The name listed 3i Atlas. The trigger, rotation profile stability and directional consistency. The action, add to Tier 3 threat observation queue. No press conference followed, no tweet, no press release. But within the community of planetary defense researchers, the update was impossible to ignore. To understand the significance, one must grasp what this list is. The threat monitoring list is not a catalogue of known threats like impactor objects. Instead, it's a behavioural watch list, a dynamic log of bodies that exhibit potentially dangerous or poorly understood physical traits. Most entries involve high-velocity spin-ups, fragmentation risks, or unstable flyby geometries. 3i Atlas, however, triggered inclusion for the opposite reason. Its rotation wasn't chaotic, it was too stable. The update followed 5 days of data correlation between ESA's Space Situational Awareness Center in Darmstadt and CNES in Toulouse. Analysts compared spin data from Chinese, American, and European sources, cross-referencing everything from light curve models to infrared harmonics and radar return timings. What emerged was a consistent profile, a rotational period of 5.73 hours, stable within 0.0013 seconds, fixed surface zones of high reflectivity, phase-locked emission events correlating with Earth visibility, a persistent thermal lag outside natural ranges, echo distortions localized to specific spin angles. Individually, these traits might seem curious, but taken together, they suggest control, an underlying system governing the object's orientation, temperature, and visibility. According to an internal ESA communication retrieved by academic partners, the decision to add 3i Atlas to the registry was based on its potential to alter course using rotational mechanics. This is not speculation. It's based on orbital simulations that showed microvector shifts, slight, barely measurable nudges to its trajectory that lined up with known spin alignments. The concern is not that the object is targeting Earth. That claim remains unfounded. The concern is that its spin state is linked to its trajectory in a way that natural celestial bodies do not typically exhibit. In artificial satellites, spin is often used to stabilize orientation or to align thrusters for course corrections. If 3i Atlas uses its rotation for similar means, even without engines, then it represents a new class of maneuverable interstellar object. This is why ESA's inclusion matters. By placing 3i Atlas on the threat monitoring list, even at the lower Tier 3 level, the agency is quietly signaling to member nations that the rules are changing, that not all objects are passive, that some may have predictive behaviors, response patterns, or internal systems unknown to current science, and that such systems, even without intent, carry risk, because they move on timelines and in ways no gravitational model can fully anticipate. The update also grants 3i Atlas priority tracking time on ESCAT, TIRA and the Galileo surveillance grid, and allows for funding of emergency observation runs should new anomalies emerge. The tone of ESA's memo was not alarmist, it was clinical, but between the lines its message was unmistakable. This is no longer about whether 3i Atlas is a comet, a spacecraft, or something else entirely. This is about preparing for the first object we cannot model with classical mechanics alone. Not because it's too fast, not because it's too far, but because it behaves. And when behavior enters the equation, so does agency. And when agency cannot be explained, it must be watched.